permit, they ask me to come in, because I'm his nice neighbor, and get a blood sample from me as well. And they get a sample of my hexokinase. We'll call it hexokinase D for Dusty and hexokinase B for Bob. Right? And they isolate those from our cells, or they clone them up into a plasmid and express them in E. coli, whatever they want to do. They get those proteins available, and the ligand is sugar. They get sugar, and they measure this, and they can do it pretty easily. Here's what they do. They add a set amount of sugar and figure out how much of it was bound. They measure this. They find some spectroscopic trick or something to figure out the ratio. And then they ask us to think about the KD and what that means. And here's what they find. They find that the two hexokinases, one has a KD for sugar of 5 millimolar, and the other has a KD for sugar of 25 millimolar. Notice it's in nice molar units. Isn't that the joy? Unfortunately, while they were making these measurements and doing all this, they mixed up the jars. And they asked me, for this KD, is it, clicker question, A, Dr. Bonham's hexokinase, or B, Dusty's hexokinase? This guy. So talk to your neighbors, see if you can convince yourself. He's having problems, I'm presumably not, with getting enough sugar into my cells. For this one, they lost the label. Is it Dr. Bonham's or Dusty's hexokinase? Convince your neighbor, click in.
A larger number is worse, so it's got to be, yeah, so it's going to be B, Dusty. For 25 is the larger. Oh, yeah, the larger.
Which one is
KD.
this one? Who's is that?
For that.
Yes, sorry. You and I were close, completely opposite what he was saying.
I like where your head is.
All right. Apparently, we're all pretty good at this one, except the person who hit C. Neither. Yeah. This one has a high KD, which means it's good or bad at binding?
Bad.
Bad. Which means it's probably Dusty's. Sucker.
Oh, brutal.
I know. But let's go further. Let's say we graphed this behavior. So here we're going to measure sugar levels versus theta, versus how much is bound. The most we could get would be 1, but reminder, we're going to asymptote. We're never going to quite reach there. And they're both going to start at 0. When you have no sugar, you have no binding. That would be magical. So if I want to draw these curves well, how do I tell them apart? What's going to be different on the graph? One will go up faster than the other, but how will I know? Where can I anchor myself? I've got a 0 point, the 50 point. So one of them is going to be at this 50% point at a concentration of 5 millimolar. And the other is going to be at a 50% point at a concentration of 25 millimolar. Good so far? So now I have 3 points. They'll eventually try to asymptote. They start at 0, and I've got this 50% point. So I'll draw here. That's about 50%, right about there. And I'll just try to draw a curve. And I'll be like, this goes up, has to go through there, and will asymptote. This one.
You need a longer board.
I need a longer board, but that's okay. Goes up.
Oh.
We'll someday asymptote. Yeah. There we go. We can now tell these apart. And there's some real insights we can get from this. So once again, the black curve is the hexokinase B from Dr. Bonham, and the blue curve is Dusty's malfunctioning hexokinase. Sucker. I'll teach you to steal my cable. I'll make fun of you to a class you'll never meet. He's a nice guy. When we look at these, notice the different behavior. At I guess I should extend this curve to make it clear. At really high levels of sugar, there's not really much difference. Right? If I go out to like the edge of my board here, there's not really any difference in the function of the proteins. If you have a ton of sugar, they both bind it. You see differences at the low level. And what's interesting is no matter where I measure, if I measure at 1 or 4 or 10 or 20 or 30 or 40 or 50, under every condition, under every condition, notice that hexokinase B binds better. It's not isolated to just low values. At any value, this one is better than that one at binding. KD is that single knob. If I say I've got a better KD, at low, I bind better. At medium, I bind better. At high, I bind better. It tells us a lot about the protein's function at all the different levels. But notice that the relative level changes. The difference in magnitude of better is very dramatic down around the KD. Whereas when I'm way up here, yeah, it binds better, but not much. And when I get way up here, the difference probably becomes unmeasurable. So the place of maximum difference is around the KDs. They tell us that too. KDs are where it really changes. That's where things matter. That's where we have the most biggest delta in these functionalities. So now we're going to be doctors. He's in. He's sick. He's not getting enough sugar into his cells. We see this graph. We label our tubes correctly and get this graph. And we need to help Dusty stat, right? Which I think means now. I know it. Now, what could we do to help him? Easiest possible solution.
Sugar.
Chemotherapy. We got it. We could give him sugar. Because let's say I need 70% saturation to be healthy. So I need that much to be happy. I need 6 millimolar in my blood to keep 70% saturation in my cells and be happy. You would need like 30. So he just needs to eat 5 times as much sugar as I do.
Well, that sounds kind of nice.
I mean, it sounds nice for a while until the other metabolic syndromes kick in.
Until he gets Alzheimer's.
Yeah, actually. But then he won't remember. So
Well,
wait, why was it
That's
sugar?
awful.
I'm awful. But again, this is how things manifest. These binding curves are how interactions occur and how we have to think about addressing different chemical problems and drug problems and all that stuff. So it's a really powerful tool to have in your bat belt. That man still has a bat belt, right? Is that dating me? Dating me. Bat, like Batman? Yeah. No, back belt would be like a fanny pack. I'm not even going to advocate for that. Okay, so that's a very qualitative example of how we can think about and use this. I still want a quantitative example. I know we're running out of time, but check it out. So here's a very real example. IgGs, which are antibodies in your immune system, bind their targets with an affinity, and this is all true, about 2 picomolar. That's a pretty common affinity. Pico is very small. That's 10 to the negative 12th, if you've forgotten. Very small affinity number. If 80% of the IgGs for a given virus are bound, how many viruses are in your blood? This is a real thing. They get antibodies, you put some blood on and titer, and you see what percentage of it congeal. You get an idea of the percentage that's bound. How much virus do I have in my blood? Should I be concerned? This is the next Ebola? This is hard for some folks, and not in a bad way, just if you haven't thought about that for a while. So talk to your neighbors. Be good friends.
got that far.
So you set up this equation where you're solving for some complexity, and then you just move that, do some algebra, rearrange it, and you get
And I was like, because I said, yeah, 2, I said, we see if any just saying it, that doesn't work at all. So, okay, I dig it.
I can dig it.
So here's the deal. It's not E. I'll just give that to you. It's not E. If you are kind of lost, hit E real quick so I can see where we're at. Oh, yeah, okay. Let's do this together in the last few minutes we got. Again, our key equation is theta equals L over L plus KD whenever we're dealing with these kind of problems. And we're going to substitute in what we know. So theta is 80%, which is 0.8, because 1 is the maximum it can ever get. That's a common thing that happens. Wrong. I don't know how much virus I have. That's a problem. They're still unknown. But I know my KD. It's 2 picomolar. Then I'm going to do algebra. I'm going to multiply both sides by the denominator. So I'm going to get 0.8 times L plus 2 picomolar equals L. And I'm going to simplify terms. I'm going to FOIL it. I get 0.8 times L plus, what's 0.8 times 2? 1.6 picomolar equals L. Then I'm going to combine like terms. I'm going to subtract 0.8 L from both sides. And I get 1.6 picomolar equals 0.2 L. So here I subtracted 0.8 L from both sides. Now I have this 0.2 to get rid of. I'm going to divide both sides by 0.2. And I end up with L equals 8 picomolar. This is the kind of math, essentially, that is done to determine what is the viral load that someone is carrying. Right? These are big things we got to solve. So that's applying the math to try to use it and solve it. We're going to continue to work with this. And on Monday, we're going to move into hemoglobin and myoglobin and all sorts of good examples of it. So read ahead, get ahead, and we'll do good things. Read ahead to get ahead. Thank you all for your time and attention. Good questions today. We need more. I'm tired of talking. Okay. You know me.
Yeah.
That's all right.
Sarah.
Yeah, hold on.
Good luck studying.
I
All right, brother. See you later.